In this video, I want to introduce you to the lab. Lab 7 is the dehydration of cyclohexanol. So in this experiment, you will react cyclohexanol under heat with an acid catalyst to produce cyclohexene. The way we indicate heat is with a triangle. This is the Greek symbol for the element fire, but we still use it. And when you have a catalyst, oftentimes that's written below the reaction arrow. So in this reaction, water is eliminated, and we don't balance this chemical equation, generally speaking, in organic chemistry, but I will go ahead and write that in anyway. All right, so in this reaction, water is eliminated. You have OH being eliminated from one of the carbon atoms, and then hydrogen being eliminated from the other carbon atom. And we normally don't draw hydrogens on carbons, but that's your water that's being eliminated. And so we form a carbon-carbon pi bond. Okay. Strong acid catalysts like sulfuric acid are normally used, which is non-volatile. That has a very high boiling point, and so it does not evaporate. We're going to use phosphoric acid, which is a slightly much less acidic acid, but it's much less hazardous, and also it has a very high boiling point, so when we boil the reaction mixture, it won't escape. So this reaction is endothermic overall, which means that the products are unfavored. So we need to shift this reaction to the right using Le Chatelier's principle to remove water. So remember that if you have an equilibrium and if you remove water, the reaction will shift to the decrease. So this reaction will keep shifting to the right as you remove water, because water won't be present to shift the reaction left, okay? So we're going to use Le Chatelier's principle to remove the water from the reaction flask, and this shifts the reaction to completion to the right. And this is really conveniently done since cyclohexene forms an azeotrope with water, which can easily be pulled out of the reaction flask away from the acid catalyst, which would otherwise cause an unwanted reverse reaction to occur. The reaction that happens in the reverse reaction is called addition, okay? An addition reaction, as you know, to form an alcohol from an alkene, but we want the alcohol to go in an alkene, and that's called an elimination, okay? So it's easiest to remove cyclohexene because it has a low boiling point. All right? So the lower boiling point azeotrope is about 83 degrees Celsius. So cyclohexene and water form a lower boiling point azeotrope of 83 degrees Celsius, and that contains a mixture of cyclohexene, which has a boiling point of 83 degrees Celsius, and water, which has a boiling point 100 degrees Celsius when it's pure, okay? And this is collected by a simple distillation apparatus. The higher boiling point cyclohexanol does not distill at these temperatures because it has a much higher boiling point of 161 degrees Celsius. And as I mentioned, phosphoric acid has a boiling point of 213 degrees Celsius. So that remains behind in the reaction flask as the reaction is occurring. So in our still pot of the distillation apparatus, we've got all of these components: cyclohexene, phosphoric acid, and this stuff here, okay? But when we distill it, and products form, we are going to form cyclohexene and water, which come out, okay, which have low boiling points, okay? And since you're removing product from the product side, the reaction is going to shift to the right. And in here, you have no cyclohexene to push the reaction backwards. So it's a little trick to isolate the product, okay? And so let's talk about the mechanism. The dehydration reaction follows a three-step mechanism. So the purpose of H3O4, which is called phosphoric acid, this is found in Diet Coke and Dr. Pepper, things like that. It's used to provide tartness. This is to protonate the hydroxyl group of the alcohol. So if we have the alcohol drawn out here, we can protonate the alcohol. And that forms, so that's P for protonation. This forms, this converts the OH into a better leaving group. And this also causes a weakening of the carbon-oxygen bond, making it more polar, more ionic, and more prone to heterolysis, okay? Remember, heterolysis is a word used to describe a situation when a carbon heteroatom bond breaks according to the direction of electronegativity. So in the next to the left, so that's a carbocation that's formed. Okay, that's a carbocation intermediate. And this is an oxonium ion intermediate. Okay. Sometimes people take the lab without taking the lecture, so I'm making sure you all know what's going on here. That's the E step or elimination step for this step here. Okay, now that we have a carbocation intermediate, remember that the carbocation intermediate is extremely acidic. It's highly acidic, similar to HCl. So this has a low pKa. It's very acidic. And you might not see it, okay? It's impossible to see it without drawing it. So I'm going to draw in a hydrogen here, okay? That is the acidic hydrogen that's on the beta carbon. Okay, the alpha carbon is the carbocation. So anyway, it eagerly releases a proton to any base it encounters in solution. We probably have water floating around in solution. The phosphoric acid is 85%, so there's 15% water in there. And this guy here is going to become deprotonated. So D for deprotonation. And what we form here in the product is the cyclohexene, and we form more H3O plus, which is, as you know, another way to write H plus. So this is the catalyst that gets formed again, and it is reborn to do more operations, okay? So we don't need 1 mole of H plus, we just need a catalytic amount. So the experimental procedure, as you will see, is to measure out 10 milliliters of cyclohexanol, add it to a 50 milliliter round bottom flask, okay? And we're going to add 3 milliliters of phosphoric acid. Okay, this is going to be the limiting reagent. So you need to use the density and the molar mass to figure out how many moles that is. We're going to add 3 milliliters of phosphoric acid. It's actually 85%, okay, in purity, concentration, and it's going to be the reactant that's in excess, okay? So you don't need to calculate moles of this or anything. There's plenty of it to go around, and remember, it's catalytic. You just need a drop of it, but we're going to just slam on this thing, all right? So we're going to put this on a hot plate and set up a simple distillation, and we're going to use an Erlenmeyer flask with a beaker in ice to support the receiver. And the ice is necessary to keep the distillate cool and to prevent the volatile product from evaporating, okay? So if we go back to this diagram here, if something has a boiling point of 83 degrees Celsius, it's a little bit volatile, okay? It can evaporate readily. So we're going to chill this whole thing in ice. That's the purpose of ice, okay? It's also toxic. the product cyclohexene is not toxic, but it has a unpleasant odor. All alkenes do. And I'm sorry you can't experience what that smells like. The lab really stinks up on this day. All right, so we're going to slowly heat this distillation up, and we're going to measure the temperature of the azeotrope. Okay, so keep an eye on that. And we're going to stop the reaction when white fumes begin to form in the reaction flask. And that's when basically there's no more reactants left and we stop the distillation. And we're going to do some workup here. So it's oftentimes necessary to draw a little flow chart in some lab notebooks. We don't have a formal lab notebook, but I'll show you what this looks like. In the product, we have water and H2O. There might be residual amounts of acid, okay? And so what we do is we add sodium bicarbonate to this. We add 1 milliliter of sodium bicarbonate, okay? And you have, so this is 10% Na2CO3. And you're going to have two phases. You're going to have the aqueous phase and the organic phase. The organic phase is going to be your organic liquid, which is not soluble in water. And your aqueous phase is going to contain all of your ions. So it's going to contain any H+, any sodium carbonate that hasn't reacted, any sodium bicarbonate that's resulting, water. Okay, this is going to be all of your aqueous stuff. Now what we do is and so we put this in a separatory funnel and we separate it. Then we add 5 milliliters of ice water and we drain that. So we wash it again. So we add 5 milliliters of water. Okay. And again, we're going to have the aqueous phase and the organic phase. And over here, we're going to have water and any residual sodium bicarbonate, which maybe was left behind in the funnel. And over here, we're going to have the cyclohexene. I'm running out of space here, so I will just go to the next page. And then what we do is we add... we take this and we put it into a separatory, we put it into a flask. Okay, so we have our flask here with our cyclohexene. And you might see a drop or two of water, maybe just a drop, okay? And what we do is we dry the organic solvent. We're going to add about a half teaspoon of anhydrous calcium chloride. So these calcium chlorides are beads. Okay, they're going to go down into the bottom layer, not really the floating in the air like that. And then we're going to filter this out, okay? And we're going to get the calcium chloride, which is going to be absorbed with the water. So remember, the calcium chloride is something we call anhydrous in chemistry. This reacts with water, and I believe this can form up to a hexahydrate. I don't really remember. So anyways, this removes water from your reaction. So it dries. Okay, this is how we dry the organic product. All right, that's the purpose of adding the calcium chloride. And so then we get a flask that contains a nice sparkly clear cyclohexene. All right. Now we're going to weigh the empty flask. We're going to weigh the flask with the cyclohexene and the product. Okay. And from that you can figure out the theoretical yield. I mean, the experimental yield is just the difference, right? But the percent yield you have to use from the theoretical yield and everything. Watch the video for that. Now, we keep a cork on this to prevent the the cyclohexene from evaporating because it's quite volatile. The boiling point, again, is lower than water. And it smells, so we know it's evaporating all the time. Now, we're going to do a Bayer test. You might wonder why we just don't call this the potassium permanganate test. Well, this was the dude that did a lot of stuff. He invented aspirin and other things. So, you know, we kind of try to, you know, name things after him, a few things anyway. And remember that the Bayer test is a test for unsaturation. It's in a previous lab, but we don't have a lab manual that we could easily thumb back to, so I'll just take it through here now. If you have an alkene, like say you have cyclohexane, and you add potassium permanganate, this is purple. So again, I just want to emphasize there's no alkene here. I didn't make a mistake. There's no alkene. There's going to be no change in color. All right. But if you have an alkene, all right, and you add potassium permanganate is, as I'm drawing, purple, okay? And when this reacts, it does a dihydroxylation. We'll learn about this reaction if you're taking the lecture. It adds 2 hydroxyl groups across the alkene in a cis fashion, so you form the cis product. Now, the important part to realize is I don't have a brown colored thing. I could find it, but I don't want to worry about this. You form, and the potassium and everything else is in there, but you form MnO2, okay? First of all, it's a solid, and second of all, it's brown, okay? It's not red like my pen color, okay? So that's a positive test. This is a negative test, okay? So we're going to add some purple potassium permanganate to this and do the test. Now, when you do this reaction, it's important to realize, and you'll see me wiggling the test tube quite a bit, and the reason for that is because you're going to have 2 layers. So this is your test tube. Let me just label all my drawings because they're terrible. Up here, you're going to have the cyclohexene, and down here, you're going to have the purple aqueous solution, water. Okay, so cyclohexene is less dense than water. It's immiscible, it floats. So I have to shake this up a lot, you know, wiggling it, tapping it and everything. And then we're gonna let the test tube kind of sit for a while. It's gonna look all cloudy. And then we're gonna see maybe some layers separate, maybe some brown precipitate, maybe the color change and all of that. So you wanna observe at the very end, okay? So I hope that makes sense. And so we really have to shake it a lot to get these 2 reactants, which, remember, the potassium permanganate is ionic, it's soluble in the water, so these phases need to kind of mix up a little bit, all right? Now, as we saw in the previous lab, we had situations with the bromine, so we're doing no bromine test today, okay? I'm going to look into, you know, the best way to do this in the lab without actually buying bromine off of eBay, so for now, don't worry about this semester, okay? It's something I have to worry about. All right, so look at the limonene lab to review the Bayer test if you need to, okay? I'm misspelling guy's name, aren't I? How do you spell it? B-A, I don't know. All right, so, and that's it. And we do the calculations. Let me scroll down here. I'm looking at my computer for the post-lab questions to see if I've addressed all of the post-lab questions. And they're blowing leaves outside, so if the lab video is kind of loud, that might be why. I might just do a fast-forward video like I've done before. So try to find a better soundtrack as well for the video. Let's see. Okay, so you're supposed to record the amount of cyclohexanol used in grams. So remember how to do that. Look at the bottle. When you do the lab, it's going to have the density on the bottle, okay? The density, the molar mass, all right? Calculate your theoretical yield of cyclohexene. And yeah, so again, we're not doing the bromine test. Okay, no bromine test I mentioned. Yeah, I've already talked about that. So don't record that on your lab sheet. Just leave it blank or write not applicable or NA. All right, what's the purpose of these materials during the experiment? Phosphoric acid we've talked about, sodium carbonate we've talked about, anhydrous calcium chloride we've talked about. Why did the procedure call for ice to chill the receiver flask? We've talked about that. Why couldn't hydrochloric acid have been used instead of phosphoric acid? We alluded to that. You might want to look up the boiling point of hydrochloric acid. Number 4, draw the curved arrow reaction mechanism for the dehydration of 2-methylcyclohexanol. 2-methylcyclohexanol has this structure right here. Well, I don't want to circle necessarily the carbons, but here's 2-methylcyclohexanol. Okay. Number 5 is to draw structures for the following. Draw the structure or name the structure, depending on if you have a structure or a name, respectively. So if you need to know how to do this, let me talk about how to name alcohols really quick. It's very simple. Now, what you do is you find the longest chain that contains the alpha carbon. The alpha carbon contains the OH. Okay, so there's your alpha carbon. So if you have a molecule like this, okay, this carbon has to be part of the longest chain. Okay, so it could go this way, 1, 2, 3, 4, 5, 6, or it could go this way, 1, 2, 3, 4, 5, 6, 7. It's got to go this way. Okay, that's the longest chain. The number, second thing you do is you number the carbons so that the alpha carbon is lowest number. Okay, no matter what. Okay, no matter what. If you have a methyl group at carbon 2 and an alcohol at carbon 8, do it the other way. You want the alcohol to be at the carbon 2 and the methyl group to be, at carbon 8. So when we number the carbons, it's going to be like this. Okay, so here's our alcohol. We're going to name this differently, so don't name that as a substituent. It becomes part of the parent. I'll show you how that works. And this right here is a 3 carbons, okay? So 3 carbons is propyl. So the name of this would be 3-propyl. Okay? And then you can write 2-heptanol. This is kind of like an older way of naming it, which is perfectly fine for me. That's how alcohols were named when I was a student taking organic chemistry. Or you could name it like this: heptan 2-ol. So the purpose, obviously, for the number 2 is to indicate where the alcohol is. And anything that ends in -ol is an alcohol. All right? So let me, my screen just went out with the screen saver. Okay, so you might have cyclic things. Okay. If you have cyclic things, the alpha carbon is always assumed to be number 1, so you don't need to show it. Okay, you don't need a number. This is just going to be called cyclobutanol. Okay, cyclobutanol. We don't need to say 1 cyclobutanol. Okay. And the other ones are alkenes. I assume you've already talked about naming alkenes, so I'm going to say see the lecture if you're in my class. See the book if you're in my class, which we've already talked about this on the last chapter. if you're trying to take the lab without taking a course, go to your appendix or your table of contents and look up naming alkenes, okay? So I won't reintroduce that concept here. I just wanted to talk about alcohols, which might be new to my class. That's it. Let's do the lab.